Yes, now it is time. So I will just do the welcome people in the room and welcome people online to this session. I'm just the in-room wrangler. So feel free to just, if you need to wrangle in the room, I'm Leslie Shee, an ESIP board member, but I'm now going to turn it over to our session hosts online. Doug Newman.
Thank you very much, Leslie. All right, so first off, I'd like to apologize for not being here in person, but I feel fortunate that I'm able to be here virtually as well, given the current situations we have. Um, what we're going to be talking about today is science data stewardship in the cloud. What NASA's experiences have been with developing an archive solution in AWS, and also what NOAA NCI's experiences have been. We're going to start off with a talk from Ben Williams from NASA ESDIS and EED, who is going to talk about the infrastructure associated with our archive solution. Then Nancy Ritchie from NOAA and CEI is going to talk about NOAA's cloud archive strategies, and then I'm going to round it out with a talk about our archive guideline recommendations in NASA ESDIS. Apologies for the kind of, I think this session's billed to be a 90-minute session, but we only have 3 talks and a discussion because a number of our talks did not get approved in time. So apologies for that, but we will kick off with my esteemed colleague, Ben Williams. Take it away, Ben.
Doug, thank you. Thank you very much. And thank you for all of the people in the room that obviously I am unable to see, but certainly wish I was there in person. So good morning and good afternoon. I'll work on getting slides shared and displayed. And comms tech check. Am I displaying before I start monologuing at you?
I can see it on the screen in the room. Yep.
Doug and Leslie, thank you. Thank you very much. My name is Ben Williams. I'm the Enterprise Solution Engineer for the EED contract supporting NASA ESDIS and their Earth Data Cloud environment, and wanted to talk to you largely around cloud cost management and the experiences that we have had, both positive and some negative, as we've learned to love cloud cost management. Thinking through that topic, it occurred to me that there is a correlation to fire, to the power and the opportunity that fire represented to us as a species, as well as the danger of fire. And a couple thousand years towards electricity, same sort of evolution, an incredibly powerful, useful tool for us, but comes with it a significant amount of danger as well. In broad terms, the cloud is a similar sort of resource for us. It's incredibly powerful, but in particular in a cost management can be considered to be reasonably dangerous. So looking at cloud computing, we're and leaning in on the power of cloud computing, the immense scale that we have at our fingertips with cloud computing, rather than having to pre-allocate the amount of resources that we go through a procurement for, we have instant access to as much scale as we can consume. We also offload the complexity of that underlying infrastructure to another party to handle, which accelerates our own innovation. We don't have to worry about all of the wiring of our data center and the heating and cooling. We don't have to hold staff to do those functions. We're able to go right to the value add services that we're building on top of it. In terms of data science applications, the analysis in place power of the cloud is incredible for us. Our Our data sets are getting larger and larger. Network bandwidth to download those data sets to university or local repositories to do analysis is getting harder and harder to maintain. But the ability to bring the compute to the cloud brings incredible opportunities for us to innovate as we move forward. But also a little dangerous. This shared responsibility model of the cloud means that we have to trust other people. We have to trust a commercial vendor with underlying security. And we run into this pay-as-you-go model. Pay-as-you-go being what we're really going to be talking about, how we have managed that pay-as-you-go aspect in the Earth Data Cloud environment. But thinking back to the corollary to electricity, the power and danger of an electricity approach. We've had 100+ years to figure out ways to conserve electricity. We want to conserve cloud costs. We don't want to be wasteful with cloud costs. There's a corollary there. We've learned through practices that we should turn off lights if we're not in the room. There's a corollary to turning off compute resources in the cloud if we are not actively using them. Otherwise, we're wasting money. Motion sensing light switches became a thing, I don't know how long ago, but it was an automation to turn off those lights for us. And there's a loose corollary to auto-scaling compute. They turn on when there's demand and turn off or at least reduce when there is not demand. Smart thermostats, I'm seeing a corollary there to intelligent tiering in terms of storage classes, which we'll talk a little bit about, and I think Doug's going to talk a little bit about as well. Circuit breakers. We developed the circuit breakers to not overload our electrical systems and protect our infrastructure. That could be said exactly for our cloud infrastructures. We have automated cost controls that diminish or shut down resources if we are in the middle of a undesirable cloud cost event. So as we're looking at that electric meter, or that cloud cost meter, we're looking at different ways to reduce the exposure, reduce the danger, manage the danger of the cloud, so that we can optimize the power and utility of it. And so for NASA, for ESDIS, for the Earth Data Cloud, a little bit of motivation for us really diving into that and getting smart about it. The Earth Data Cloud is a broad, large, complex ecosystem. There's over 500 individual developers contributing to the Earth Data Cloud and its applications, all making individual decisions that have an impact on overall cost to NASA. Those developers are in over 250 individual AWS accounts. Those are the individual siloed billing units in the cloud. Over 400 HTTP endpoints, certainly not over 400 production applications, but those are the endpoints even in our SIT and UAT environments, which still have the potential to incur unexpected cost. We have over 140 petabytes of data stored in AWS S3, around 85 petabytes today of science data, or at least primary science data, and then there's backups and copies of some of that data along with management data. And Doug's going to talk about that a little bit more. At any given time, we have more than 1,000 individual EC2 instances doing any number of processing over science data or running applications for us, spread across over 70 individual AWS services. So there's so much scale and complexity in our ecosystem. We had to level up. We had to get better at how we were looking at cloud cost management. because a old traditional model of, well, we'll just check everything and make sure everything is working, stopped really scaling the number of people involved, the number of micro decisions that were being made. We had to protect against the unintentional, the unexpected, and even the malicious use of our environment. There's a little corollary there to cybersecurity being something that we are all working to protect against, but in the cloud, there's also a cost exposure for denial of service just by accidentally running out our cloud budgets. So as we look at that, we developed a set of cost management pillars, how we kind of look at the ecosystem, how we divide up the portfolio of things that we're trying to improve in order to handle this powerful and dangerous beast of cloud computing. Estimating what our future costs are going to be. We identified that our estimation processes needed to mature, and we'll talk a little bit more about that. Monitoring, which is honestly where a lot of people in the cloud start and is a good place to start, just being able to see all of the different costs that are being incurred. Protection mechanisms, both human processes and also, where appropriate, automated processes to help avoid those cloud cost overruns. And with all of this data at our fingertips, all of these big and small decisions being made, trying to optimize our cloud costs, making smart decisions for where our cloud cost dollars go. We'll talk about each of these a little bit as we proceed, but all of this comes down to data. It's all data and information. And it occurred to us that as the Earth Science Data Information System for NASA, we're actually reasonably good with data. We handle data all the time. And so in a similar mindset as perhaps cybersecurity and SIEM systems, where they are integrating data from multiple sources in order to make the best decisions for cybersecurity, as well as what we do for Earth science data. We said, let's bring a similar sort of mindset to how we're managing cost. Let's bring cost data in from a variety of different sources, those budget information, usage information, inventory of our cloud resources information, and bring it into a data analytics system that we can then do data mining on, that we can ask questions of, that we can generate forecasts from. This has been incredibly powerful for us and useful at our scale to treat cloud cost management as a data science project. So we're in this world where we're doing comparative analytics between what our forecasted or budget approved costs are versus what we actually see in practice. We got to a place where we were comparing the cost of a new application that we were delivering to a similar application that somebody else built in our ecosystem. We have enough data that we're saying, hey, your application is doing a similar thing, but costs twice as much. We were able to ask more interesting questions because we had that comparative analytics capability. Anomaly detection, walking into a machine learning, statistical forecasting area allows us to identify what are blips of cost and what are actual cost spikes, and which of those do we really need to be paying attention to and reacting to. We also want to be looking at what resources are out in our ecosystem. Are they being used? Are they just sitting there and not being used? In an ecosystem as large as ours, it's very easy for there to be small systems out there that are just not doing anything at all, and trying to identify those and shut those down. But again, looking at the cloud cost management problem as a data science, a data analytics problem, and using some of the same tooling and approaches that we would in those domains. Digging in a little bit on our estimation process, what has worked for us. On the left-hand side, you're looking at just a cartoon of the chaos that is developing a budget in the before times, where it's phone calls, it's Excel spreadsheets, it's emails, all kind of jumbled together to figure out what a basis of estimate is, what someone is approved for going forward in the cloud. We realized that the estimation process was a key link in the chain that we needed to modernize in order to approach the cloud cost management problem as a data science problem. We had to get cleaner data on the estimation side into our system in order to be able to start doing the rest of our work. That begat the Cloud Resources tool, or our CREST tool. So it's an in-house web interface for the aggregation of cost basis of estimate information, and then an approval workflow along with reporting out to NASA financial systems. That CREST application, like I said, basis of estimate, we started with honestly a relatively rudimentary basis of estimate. This year graduated to basis of estimate based on historical actuals. We've been operating in the cloud long enough that we can start looking at the trends of utilization from prior years in order to be a strong indicator of a basis of estimate for future years. So we were really excited to bring that to bear just this year. Also new this year was the concept of organization-wide egress thresholds, and we'll talk a little bit more about that. In the before times, egress was something that we were particularly concerned about for each individual application. The statistics bore out that honestly we would be better to look at that at an aggregate or an organization-wide level versus individual applications. Kind of overfitted when we first started. We are looking at cost efficiency KPIs and seeing whether or not, for instance, our management systems are scaling linearly with our growth in science data, or whether or not there are economies of scale. So we're evolving each of these as we learn more about the cloud. But this Cloud Resources tool has allowed us to do some kind of more sophisticated analysis than if the only thing we were doing was monitoring cloud cost actuals. On the left-hand side, you're looking at sampling of what budget approvals were for the aggregate of our ecosystem versus how much we were actually using. That's the orange bar for the budget and the green bar for what we were actually using. So we were underneath what our budget approvals were for the cloud. There's pros and cons to that, but we had that information. We had that information instantly available to us. We started generating machine learning forecasts for all of our different applications and are now looking at the error bars. How can we decrease the error bars of our future forecasts, our budget requests coming in above our forecasted error bars? Are there odd anomalies we need to dig into? On the egress front, egress is one of those items that, granted, is not a very large cost for us. It's one of the most unpredictable. And so we, for a long time, looked at egress in terms of individual applications. What is an individual application's expectation for its egress? And if things went above that, we would start to take automated protection actions. That ended up overfitting a little bit, though. We started looking at are major science data distributors who had petabytes worth of data being distributed from the cloud using the same sort of rubric as our very small applications who might be not even getting to a terabyte. Understanding that overfitting put some challenges on our application teams. In recent months, we've modified from individual application egress monitoring to an organization-wide egress monitoring. It means that our automated protection mechanisms aren't firing when they don't need to, based on an aggregate look at our Earth Data Cloud cost profile. And it's working great. We have had in prior times some individual applications that had unusual spikes that were corrected by our automated protection mechanisms. But this particular spike, if you're seeing the line in my mouse on the left-hand side of the screen, was a tiny application. This was not something that cost us much money at all because it was a tiny application. Looking at it from an aggregate standpoint, it's just a tiny little blip. And our overall egress allocation is looking just fine. That helped reduce pressure from our individual application teams and reduce some of the operational burden of, well, we throttled or cut off an application and spent a bunch of time unthrottling it when the truth of the matter is it was just a blip. So that was an example of something that when we first started seemed totally logical, but as we have used the cloud and gotten a little bit smarter and trusted our statistics a little bit better, we were able to take a broader organization-wide level view. A little bit more, and I'll, let me see, wrap up here in just a couple minutes. On our automated protections, we're talking about those egress limits. We're talking about how we certainly have triggered those in the past for less urgent cost events. But there's still room to go to refine those automated cost protection mechanisms. Anomaly detection is one that I'm particularly fond of, to at least notify people when something unusual is happening related to cost impacting events. Management reserves are NASA sponsors have some management reserves that probably need to be taken into consideration for those automated triggers. Things like moving cost warnings to the left in the software development cycle, even at build time. We've toyed around with a couple of tools that would tell us, hey, there's a cost estimate that the number of EC2s that you are spawning, the number of Lambda functions in S3, looks like your cost will be about this. To give that information to the individual developers as they are making decisions in their code. They're never precise, but at least providing that information to individual developers rather than just looking at it on the back end. Also looking at optimization for our cloud ecosystem. Doug is fond of talking about the theory of constraints and looking at optimization opportunities with the biggest bang for the buck. We looked at S3 storage costs, which, as you can see on the right-hand side, over the last 12 months, nearly 60% of our overall cloud expenditures. So making an improvement in our S3 storage costs was going to be a big deal for us. We certainly focused on that, and we'll talk about that in the next slide with intelligent tiering. EC2 instances and RDS instances were respectively the next two classes of service in AWS that are adding to our overall cost. And reserved instances or compute savings plans were enacted to help reduce each of those. We're right-sizing RDS instances. We're investigating whether or not reserved instances for RDS might reduce that slice of the pie as well. CloudFront are one of our primary out-of-cloud HTTP egress mechanisms, negotiated rates and discount programs that AWS offers to scientific research institutions. But looking at the primary drivers of our cost and seeing what options we have to buy down cost in each of those. S3 intelligent tiering was one of the great successes over the last year for us. Intelligent tiering based on usage patterns for your data automatically moves that data into slightly cooler and less expensive storage tiers. We opted into all of the synchronous access storage tiers because we didn't want to have a negative impact on end users, but did want those cost savings. You can see on the chart on the left, this is overall cost on a similar board as overall storage. And right around November or December of last year, the overall cost took a nosedive while storage continued to increase at basically the rate it had been for some time. That's because data rolled into the archive instant access tier at much lower cost because it wasn't being accessed nearly as often. Comparing that to S3 standard costs, which had been what we'd been using since we started for almost all of our science data, we are seeing over a 50% savings with that change to S3 intelligent tiering. This is a relatively minor change from a technical and process standpoint, no impact to end users or applications. It's a transparent change to them. So it was definitely in that low effort, high return bucket for us. Significant step that we took last year. And to close, just a parting thought in the comparison for power and danger in fire, electricity in the cloud, the value, the utility, the capabilities of these various tools, but also the potential for misuse or negative outcomes. Artificial intelligence is the thing that a lot of us are trying to figure out. How do we reap the best benefit from? How do we use artificial intelligence to its best effect while managing and watching out for that downside? Can't say that we have all of the answers or governance around AI yet, but I know that ourselves and folks at ESIP are engaged in trying to figure that out as well. And I'm excited to see where that goes. Ladies and gentlemen, Doug, thank you for the opportunity to speak with you. I look forward to the rest of the session.
Thank you very much, Ben. I'm going to give you a virtual round of applause there, and there are some more as well. Given that we only have 3 presenters, I think we have the luxury of taking any questions as the presentations happen. So does anybody have any questions for Ben before we move on to Nancy's presentation?
Thanks. We're pausing here in the room, but do let us know if you see something online that we don't see on the screen here. Okay, in the room, any questions? Oh, yes. Jill, would you read it out, please? Could you send the microphone that way? The fellows are helping out here.
Question in the chat. Do we physically have greater than 500 developers for EDC?
Yes.
Not
I
going to
couldn't
tell
give
you
you
how
the
many.
exact number today. I'd have to look that up, but yes, more than 500 people contributing to the application development of all of the applications hosted in the Earth Data Cloud.
All right, we have one in the room here. If you maybe could say your name before you ask the question.
Yeah, no worries. Thanks, Ben. This is Ryan Abbott with Elma 84. Had a question around access patterns. So do you suspect that the I'll say rates of data ingest are you anticipating an increase based on upcoming access pattern changes to the way that people are accessing the data?
Data ingest, I'm anticipating an increase just because of the scale of missions that are coming up. NISAR in particular is going to be huge from a science data ingest standpoint. I'm also anticipating a dramatic increase in the size and number of requests for our data as artificial intelligence becomes more and more commoditized, easier to use. I'm anticipating that some of our largest consumers of our data are actually going to be AI agents. And that may dramatically change the paradigm of how our systems have to respond to an evolving world of data science. We're trying to get ready for that, but don't know where that's going to go.
And one follow-up, are you guys doing any work related to the file formats that may help reduce the overall egress of that data by allowing users to take smaller portions of the files?
Certainly, and I know that's often large conversations at ESIP for cloud native file formats, and to what degree tools like OpenDAP or formats like ZAR help in that world to allow our users to get at the same science data they need, but with less and less network overhead and back and forth exchanges. An area of active research for us, and something that I anticipate will continue to evolve over the next several years. I think our NOAA presenter might have some comments in that in her presentation as well.
Thank you. I do see Ken Casey has his hand raised. If we have time for that, let us know, Doug.
Thanks, Leslie. Yeah, Ben, did I hear you right when you said that your egress costs were relatively small?
Yes.
And did that surprise you guys? I mean, is it largely because your users are mostly internal people working within your overall cloud environment, or was it a surprise that egress costs were so small?
So our egress volumes are large. So we are between 5 and 10 petabytes worth of data leaving the cloud through CloudFront a month, and those volumes continue to increase. I think May and June, the last ones that we have complete months records, were the highest distributing months that we've ever had. And so from a volume standpoint, it continues to increase. It's just that it's being compared from a cost standpoint to the cost of holding on to that data. The just storage costs are dwarfing our egress costs. But our storage costs are far more predictable. We know when missions are going to launch and when they're going to send us data. The CloudFront public egress costs are probably our most unpredictable because none of those people who are pulling the data work for us. So surprise events can happen.
Yeah.
We anticipated that those surprise events were going to be more frequent and more severe than they turned out to be. But it still remains an unpredictable variable for us.
And have you ever explored like working on a fixed rate egress sort of relationship with your AWS, right? So that, we have something like that in NOAA NESDIS, but it's kind of subtle and nuanced sometimes too. But is that something you guys have explored?
We have explored and not landed. We have alternate negotiations related to egress, but we haven't gotten to the point where we have just a fixed egress.
Okay.
It'd be
Thanks.
far easier to predict.
Yeah,
or take
exactly.
advantage if we did.
Yeah, that's one of the big appeals for it.
Okay.
Okay.
But we do, Doug, sorry, we do have one more question. Could we get to it in the
That's
room?
the last one.
The last one.
I
Okay,
knew
last
I
question.
knew I'd regret interleaving questions with
Yeah.
sessions, Leslie.
Okay, yes, please introduce yourselves to the speakers.
Thank you, Doug. This is Mark Reese with Element 84. So,
Also, no.
yeah. So Ben, you said something earlier, and I've heard this a number of times over the last few weeks about the storage costs being quite large. As a percentage of the overall budget, it's large. To me, and it's like it's being communicated as if that is a bad thing. But to me, it kind of feels like that is the point of what we're doing here, is to store the data and make it accessible. And obviously that cost is going to go up as we store more and more data. So can you talk about what are the conversations that are happening, and are we digressing if we move the data into a cheaper storage format or facility, whatever, but it just costs more, or there's a delay in getting it back out into something that is accessible by the users? Doesn't the fact that we keep launching new missions and having new data, obviously it's going to go up, and is it a bad thing?
So I think it's a bad thing if it becomes a wildfire that's out of control versus a combustion engine where it's controlled very intentionally. We do have new missions launching. Those missions support scientific research. That's a wonderful thing, and it's going to cost some money to have that storage in cloud environments where people can reach it. But we have to be careful about that resource. It's our largest single contributor to cost. So where there is waste in that one line item of cost, that's a big element of waste. We need to be very intentional with how we're managing our cloud storage. That's managing it on the back end. We could also just stop launching so many missions, but I don't think that's the right answer.
Thank you.
And we have decreasing budgets as well with increasing storage. So if we don't figure out a cheaper way to store this, then we're not going to be able to store it.
Yeah.
Okay, Nancy, take us away with the NOAA perspective.
All right. Please let me know if I am sharing my screen, because I can't see it once I share it.
It is
Okay.
showing, yeah, it's showing on, is everyone in the room okay with how things have been? Okay, good. Thank you, Nancy. We're good.
Thank you, Leslie. All right. So I'm Nancy Ritchie. I'm the chief of the NCEI archive branch. Ken Casey is my co-author. As you already heard, he's got some questions there. He is my division chief. The other author, and I'm putting that in quotes, is Gemini, which is Google's AI tool that NOAA has recently received access to. So Doug reached out to Ken and asked if we could do a presentation, and Ken and I looked at the abstract and we thought, oh, we got this. And then I saw the other presentations this morning and thought, well, maybe we don't have this. So I need to put this into context. And NOAA is moving to the cloud, and the archive is moving to the cloud, but it's a part of this huge effort to move all of NESDIS, which is the satellite arm of NOAA, to the cloud. So it's not just the archive, it's all of the processing of the data, all the access of the data as well. And so it's a huge organizational transformation, and it's it's huge in the sense that it's a change in the culture, in the governance, in our concept of operations, as well as just technology. So some of these questions that are being asked, like the cost, I'm not privy to, because somebody else within the organization is actually doing that aspect. So with that in mind, I will get started. So Ken and I looked at the abstract for this session and we came up with some ideas. So some of the key points of the session is cloud-based stewardship, some commonalities, what's evolving, risks compared from the cloud to on-prem. And we came up with a good list here. Disaster recovery, which we are familiar with because last fall, NCEI here in North Carolina, we had a disaster and we were offline with 2/3 of our archiving systems. We were offline for a couple weeks. Now the risk is leveraging the AI. It can be scary for some, it can be exciting for others. There's that cost management aspect, and then there's the skill gap. How do we reskill or upskill our current scientists and users and make them, help them prepare for the cloud? So how will the cloud help us maintain and protect the archives? There are some AI-driven solutions. There are evolving governance, which I mentioned, and that's a huge piece. And there's also the extensible and shareable catalogs and knowledge graphs that we can share with our partners at NOAA and USGS and other federal agencies. And then experience with the cloud archive system and our future plans. So as of December of 2024, the cloud archive was actually put in production. And we have a few data projects running through that now. And as we go along, we'll actually increase the number of projects and data streams that are in the archive, the cloud archive. So most of our experience is still on-prem. And then again, some of the upskilling. So a brief history, it's been about 10 years from a pilot project back before the NOAA data centers actually merged into NCEI. And that started in 2014. And like I said on the previous slide, in December of 2024 is when we got the cloud archive into the production tier, and it's operational in the Nestis Common Cloud Framework, the NCCF. So you can read these on your own, but we had a couple pilot phases that we went through. And if you're familiar with CLASS, which is one of our larger satellite-focused archives, that was started to be migrated into the cloud in 2021, but mostly a lift and shift, as opposed to building out a brand new archive. So we call the archive the Open Information Stewardship Service. We call it OIS. It's LOIS without the L. A simple definition of what that is a data workflow manager that we use to archive data, steward that data in the cloud, and extract and populate metadata and catalogs. The technical definition is it's really a data orchestrator that leverages Amazon cloud technologies. We update those on a fairly regular basis to make them more efficient and improve cost savings. We use the enterprise services that are within the Nestis Common Cloud Framework. We use knowledge graphs within a semantically enabled linked open data framework, and we ensure full provenance in a scalable, repeatable, and transparent platform. Now that really helps NOAA achieve its strategic objectives. NOAA is really pushing us into the cloud, and it's crucial that OS is operating at the speed and scale that is required by current demands, but also future demands. Just like Ben was saying, there are going to be more data within the NASA archive. We are looking at, you know, quite a bit of increase in our data as time goes on, especially with unmanned units, whether it's in the air or on the sea or on the land, actually sending us data at huge scales. Its integration with the semantic web and linked open data approaches is also essentially meeting legislative mandates of being cost effective, but also the requirements of gold standard science and PAR 2, if you're familiar with those legislations. We need to be, the science needs to be reproducible. So this migration to the cloud offers us a unique opportunity to adopt these industry best practices and improve how we steward our data. And leveraging those AI capabilities, we are looking forward to doing that and helping us in the future. So this is a quick look at the OS workflow diagram. You can see from left to right where the data just flows across that light green area, and you can define your tasks, moving data from outside the cloud environment into the trusted environment, the archive, the access buckets, populating catalogs, populating the knowledge graph, and that's where we can start working with some of these tools, these AI tools. The pink boxes, you can incorporate this workflow in the science code, the science processing code, either a little or a lot. And depending on how you do that, really determines how much of your provenance is saved within that knowledge graph. Every step of the way is documented. Every result in the step is documented. So it's got full provenance, whether you decide to use it or not. So on the right here is just an example of what does it mean to have a knowledge graph, and what do you put in it? And I have this data file, and what does that mean? But it's really, like I said in the previous slide, we're creating full provenance and transparency of the data and what has happened to that data. You can customize your knowledge graph, your graph for your particular data project. You can add information later. So if somebody else finds a unique feature about your data, they can add that to this knowledge graph. So it's full provenance, transparency. It enables complete scientific reproducibility, which is part of that federal mandate. It is AI enablement and linked open data because of that self-documenting file or information that we put within that knowledge graph that is harvestable by machines as well as humans. So on this slide, down at the bottom, we have the OS Marketplace next to that red box. So what is that? Well, we are just getting started on utilizing this AI-powered interface. It will be a game changer for us. So right now, if you have to create a archive workflow, you have to do all the work yourself. You have to figure out what your workflow needs to be. You have to write the code to do that. However, the OS Marketplace, you can ask it. Do you have, what are your features? What are your services? Can you create a workflow that does this, that, and the other thing that I need? So this OS Marketplace utilizes the information in that knowledge graph to then allow you, a user, to query and generate the workflows, et cetera, discover the archive records, look at the metadata. And that is really a game changer for us, that you can leverage that marketplace and generate and customize those workflows. So initially it's not, we just have implemented it, so it's not going to be working intelligently right out of the box. As you know, when you just do a Google search, if you did it last year versus and then the same search this year, you're going to get different responses. You're going to get a much deeper, richer answer today than you did last year, because there's just more information out there. And by the way, this image here is generated by Gemini based on the queries I was giving it, or the requests I was sending it. So key elements still under consideration is disaster recovery in the cloud. What is the optimal replication strategies? There's many that they were talked about yesterday in some of the sessions I was in, but also today. There's ongoing evaluation to determine the most robust and cost-effective approach as well. So we're thinking about it. We're considering all options. Currently, we are just in one region. Then there's the cloud archive cost management. We have to determine the comprehensive cost of archiving in the cloud. And it's an ongoing analysis. And there are quite a few thoughts and considerations that we need to think about. Some of that was asked of Ben, if you've got data that's in deep storage and you have to bring that back up to for user requests, then that may not be the optimal approach for that particular data set. Whereas another one may just need to sit there in deep storage, and that should be sufficient. So it will be ongoing to figure out what is that balance, and then what would be the long-term goal based on our budget. Some of the challenges right now, we've got quite a few challenges. Like I said, NCEI was in charge of the archive. We did all the data management, the governance, and ourselves. And now that we are expanding that as part of the NCCF, we have to evolve that governance. We have to involve other people within our NESDIS colleagues who may not be aware of some of the requirements that we have, or some of the best practices that we put in place. And so establishing that clear governance framework, it's going to be a continuous process, and not just within the architectural development, but also as we move forward, trying to work with our colleagues and educate them and come to agreements, roles, responsibilities, that sort of thing. And then the interdependencies. So currently, if you have a new satellite go up and the data goes into our on-prem system, that data gets moved around quite a bit. You have probably at least 3 copies and on different on-prem systems. In the cloud, there will be 1 copy. And so one copy that's active for use. So how do we work with that? How do we ensure that we don't have any mistakes, any accidental removals, changes of data? So we will be working on those. So these challenges highlight the complexity of adapting traditional archive practices to a cloud environment, along with the education of people, our colleagues, who are not necessarily familiar with these sorts of practices. So I've mentioned this a couple times with our colleagues and educated them. This is really a cultural transformation. It's key to this cloud adoption. And, first off, the technological adoption. The technology itself is, relatively speaking, easier to implement. But when it comes to people adopting those technologies, you need to help them with that adoption. Having the early adopters go first, they can show success and then they can actually help their colleagues then adopt that same technology. So that human element is and can be a significant challenge. But again, we have to foster that cultural evolution within the organization. So training. We've had multiple training sessions on OIS. How do you write one of these workflows and what that really means? Next month, we plan on having a training session for people who are not developers so they can understand and help their staff with developing these workflows, or at least understand what they're trying to do. And then time to integrate that training, time to integrate that technology. You can't just learn about it and then implement it. You need some experience with that. Just like, we were given access to Gemini a couple of weeks ago, and many of us are using it to generate documents or improve the language on some of our communications, or like I've created some of these images. So we have to give people time to actually adopt. And with that, I will leave it to the questions.
Thank you very much, Nancy. No questions online. Do we have any in the audience, Leslie?
Okay, let's see here. Well, first of all, a round of applause. And we do have a question. Chris, please.
Yes, hi Nancy, Chris Lenhart at NCAR. Thanks for that. It's very interesting, very exciting developments. Just a question of clarification related to the cloud data stewardship with the leveraging for the marketplace, leveraging AI. Is that primarily for the stewards, or is it also a user-facing kind of thing, for search and retrieval?
Initially, it's for the stewards within our developer group. As excuse me, as we build it out, though, and put a pretty dashboard or interface in place to really help external users, it would be used externally as well. I don't know the time frame on that, but that is our future plan.
Thank you. We can go to the online question with the raised hand.
Hello, Nancy. This is Bhaskar Ramchandran. I'm the project scientist for LADS, which is one of the DACs in Goddard. So great content. This was probably one of the first presentations where I heard the words semantic web, linked open data, and knowledge graph all mentioned, which is a rarity. So having said that, I'm curious, what ontology are you sort of feeding off of for your work, if at all you're using an ontology?
I'm gonna call on a friend. So Ken.
Yeah, sure. There is no specific require. This is one of it's the two-edged sword of the flexibility of the system we built. So the OS, the Open Information Stewardship Service itself, does not demand that you use one particular ontology or control vocabulary. But it allows the users to indicate which ones they are using, including their own custom ones. We have a lot of groups around NOAA who have sort of their own custom community specific kind of things. Then there's other groups that use more widely, that leverage more widely used ones. OS itself is agnostic to that choice. One of the feedback points we've gotten from our initial science stewards who are implementing their workflows within OS is, that's great, love the flexibility, but could you help us out a little bit more? Could you direct us a little bit more? Don't just leave the playing field completely wide open. Give us some guide rails, I think is the terminology they used.
Mhm.
So we haven't established those yet, but that is something that we will be working on.
Okay. All right. Thank you.
Thank you, Ken.
At the moment, there are no raised hands in person.
Okay, I'm
thank you.
gonna share my screen then. Thank you very much, Nancy. So gonna get
Looks good.
a verbal. There's the verbal I was looking for, Leslie. Thank you very much. So my name is Doug Newman. I work on the NASA ESDIS project as the Science Data Systems lead at Goddard. I'm going to talk to you about how our archive guidelines have changed or potentially changed from moving from on-premises archives to the cloud and what we've learned in that transformation. So we're going to look at the traditional approach to archival, how the cloud might change that, and also how the rapid growth of our archive, as Mark pointed out earlier, might change that as well. So the traditional approach to archival is the 3-2-1, 3 copies, 2 different media types, one of those copies in a different physical location. And that methodology is basically trying to address the following risk: accidental or malicious deletion or corruption, hardware viability and cost, and natural disasters. Hardware viability being the end of life or obsolescence or failure of a particular media for storing the data. So that gave us the 3-2-1. In order to mitigate all those risks, we use 3 copies of the data, 2 different media types, and 1 copy at a different physical location. So here is that correlated to a risk mitigation strategy. Disasters. When I first gave this presentation, I had disasters as medium, and then, as was pointed out by Nancy, Noah went through a natural disaster that affected their archive. So we've now put that, sorry, the likelihood changed from low to low medium. Severity has always been high. And we mitigate that issue with a copy at a different physical location. Hardware viability and cost we see as medium or low severity and likelihoods, and we solve that by 2 different media types. And accidental or malicious deletion and corruption we solve by having 3 copies of the data. To note that we have very few examples of accidental deletion or corruption, and have never had an instance within ESDIS for the past 30 years of malicious deletion recorded. So how does the cloud change all this? So yes, we can have 3 copies of the data in the cloud, but we have no control over what kind of media types they use. And we have limited control over data at a different physical location. They will allow us to store data at a different physical location, but we have no control of the separation between the 2 locations of the data. However, our cloud services give us an incredible amount of durability. AWS, Azure, and Google Cloud all provide a standard 11 nines of durability. That's something we can't even come close to with an on-premises solution. So they was quoted as saying, if you store 10,000 objects, we may lose one of them every 10 million years or so. That's a little bit difficult to quantify, but our real example And when I originally put this slide together, we had 1.7 billion items in AWS, 1.7 billion objects. We now have over 1.8. We can expect to lose one object every 500 years. And if ESDIS lasts for 500 years, I'll be very impressed. So the cloud vendors also give us service level agreements associated with their services. And it's all down to, if we lose your data, we will refund you the cost. But if they lost our data, that is a risk. Having said that, in all the history I could find of AWS outages, none are related to S3. And I can only find anecdotal evidence of AWS lost my object singular. So the risks change a little bit for archiving on the cloud. We still have accidental and malicious deletion risk. We still have natural disasters as a risk. The hardware and viability and hardware cost are abstracted away from us. We don't know what's going on under the covers, how they're storing it. But we have two new risks: cloud vendor viability and cost. Would our cloud vendor go out of business? Would our cloud vendors suddenly jack up the cost of their services that we can no longer afford it? So with that, we have a changing risk scenario. Disasters remains the same. Accidental and malicious deletion and corruption remains the same. Cloud viability and cloud costs come into the picture. So cloud viability, similar severity and likelihood to hardware viability. Same with cloud costs. Our disposition towards cloud viability is to either accept or mitigate it. We could accept it by just being satisfied with the 9 nines and work on the assumption that AWS is not going to go out of business. Or we could mitigate it by storing it in another cloud provider like Azure or Google. And the costs we can mitigate by tying down to long-term cost contracts and freezing the cost for a period of time. However, as I mentioned earlier, we are also subject to a rapid growth in the amount of data that we have to steward. And that brings in the economic view of our archive guidelines. You've probably seen this graph in some form or another, and this is showing the quote unquote hockey stick growth of earth science data that has been and will be stored within ESDIS. We're roughly at about 140 petabytes right now, and that little picture of a satellite is NISA, which I am reliably informed will launch next month, I think, but it's been delayed numerous times before. But that and a number of other missions are going to rapidly increase the amount of data that we need to archive. So NISA alone, over its lifespan, will generate 140 petabytes of data, not taking into account any possible extensions of its nominal lifespan. We actually have in our archive right now roughly 140 petabytes of data. So we're talking about doubling our archive with one mission, NISA. So I've asked this question of many people, from high schoolers to seasoned earth scientists to my mother. How much do you think it costs a user to store 140 petabytes of data in S3 standard for a month? The only person in this audience who can't answer this question for me have either been asked this question before or are Chris Stoner. Any guesses?
Any guesses?
I didn't hear that.
Okay, wait. Rich, what was her number?
5 million.
5 million per month.
All right. That is not bad. 3 million per month. Most people are shocked by that. Now, of course, NASA has negotiated rates with AWS. We also use cost reduction techniques like S3 intelligent tiering, as Ben alluded to in his talk. But then we generally distribute 11% of our archive a month. So it goes up to 3.8 8 million per month. So can we afford 3 or even 2 copies? No, not for NISAR. So how do we combat that? So as Ben pointed out in his talks, we are utilizing S3 intelligent tiering. Shortly after we started doing that, and we finally got data into the least expensive tier, we were recording savings of about 66%. Ben has more up-to-date numbers, and that's leveled off to about 50%, but this mitigates some of our cost risk. We're also looking at putting data into cold storage, and Nancy touched on this for NOAA as well. We can realize further storage savings by putting them into storage tiers where we can't immediately access the data. But that causes all sorts of problems for applications that use the data, are expecting to get that data immediately. So we've got to develop new access mechanisms to facilitate that. It's worth mentioning, though, that back in the dim, distant past, all of our data distribution was through asynchronous patterns. We used to ship people CD-ROMs or D3 tapes in the mail. So we've done this before. We can further reduce costs by adopting the strategy of our goal is not to store copies of data. Our goal is not to lose data. So something like S3 versioning, a managed service within AWS, it doesn't back up all the data that comes into a bucket. If somebody tries to delete some data or update some data, it will then do a backup. So backup on demand, if you will. So in workflows where it's not routinely routinely we don't update the same object multiple times, or we don't delete a lot of data, and that's certainly the case for Esdis, this becomes a very attractive proposition in cost savings on storage. And it could mitigate with other precautions as well, the accidental or malicious deletion, because the data isn't actually deleted, and we can review those deletions to make sure that they were done legitimately and not by accident or by some bad deed. And the same for updates. We could also reduce costs by doing selective copies. Some data we might not need to copy. It could be recreated from sources. The L0 data could be used using the same algorithms to produce the higher level products to reproduce the higher level products. Or it could be stored with other agencies. We could rely on their copy as a backup. So what I'm going to give you now are our current conclusions on this with the following disclaimer. We are subject to change on this. As we figure this out and test these ideas out, they may change. So first going to talk about 2 tiers of data. We have tier 1 data that satisfies one or more of the following conditions. Data doesn't exist anywhere else. The data cannot be derived from other data, and it's high use data. I'm going to define high use data as the converse of low use data. I'm going to define on the next slide. So tier 2 data satisfies one or more of the following conditions. The data exists at another agency or entity. It could be reconstructed from tier 1 data, or it's low use. At the moment we're thinking about that would probably mean that data from that collection hasn't been distributed in a year or more. That could change as we go further through this. And of course, data can evolve from tier 2 to tier 1 or tier 1 to tier 2, depending on the situation. Data retention guidelines may dictate that a data set goes from tier 1 to tier 2, and there are mission life cycle transitions that we need to take into account as well. So here is our tier 1 strategy. To mitigate against disasters, we rely on multi-AZ cloud storage in S3. For cloud vendor viability, we're either going to accept or keep a copy with another cloud vendor. That is very much bound up on how much budget we have for this. And as I've alluded to before, our budget has contracted significantly recently, so we may just have to accept this risk. Cloud vendor costs are mitigated by the long-term contracts. An accidental or malicious deletion is going to be mitigated by S3 versioning and MFA deletion. This is subject to change. The tier 2 strategy is very similar, but it differs on our cloud vendor viability and cost mitigation strategies. We will retrieve or can reconstruct data from tier 1 data. And that is my presentation. Any questions?
Thank you. We just did some applause and I see a hand raised in the room. Please introduce yourself.
Hi, Doug. This is Joseph Kennedy at the University of Alaska Fairbanks.
I'm familiar.
Yeah. So I'm curious about effectively the crossover cost of the engineering effort required to get there versus saving the $1 million, right? Like we got $1 million, but we now need to build all these asynchronous services. That's like 5 developer years, right? For a single developer. So like how much, like when do you actually make that payback in these savings thing? Do you know that when that crossover time is?
In about 499 years, just before we lose that one object. We are taking that balance into consideration. So we're gathering metrics to determine that. But I think at a macro level, assuming that there is going to be a longevity to ESDIS, and it's been going for 35 years so far, and hopefully will continue to go on, that consideration becomes less and less important with the longevity of the project and the longevity of the data. Having said that, technology is evolving rapidly, so all of what I said may be thrown away due to some advance in technology in this area. So that's a long way of saying I don't have an answer to that question, Joseph. Sorry.
Thank you. All right, everyone. Any more questions, either in person or online? Is there anything in the chat? Okay. Oh,
Ken has his hand up.
Yeah, thanks, Doug. I've been wondering about this because if you kind of look back in time, right? We've been in this for more than 20 years together, basically, and over that time we've really benefited from Moore's law. Even though our data volumes have been skyrocketing, our budgets have all essentially been flat or even reducing, in real terms due to inflation. And we've survived to this point, right? Now, of course, we're transitioning into the cloud, and I don't know if Moore's law is really a thing anymore, or if it's a thing in the cloud. But I do know the cost. People have looked at this. I don't know what it is, but like AWS costs have decreased many times over the last several years. And I'm just wondering if you guys in all of your cost modeling have tried to project out, say, the next 20 years, not just based on your data volume growths and like current AWS costs for storage, but projections of what their cost for storage might be in the future as well.
We have not, but it's a very a very viable question. Recently, I was giving talks to high schoolers about what ESDIS does, and I was using, how to quantify what 140 petabytes was. I mean, it's very difficult to, even for us, to get a sense of what that means, because it's a huge number. So I just pulled a 1 terabyte hard drive that you can buy in Best Buy out of my bag and said to these high schoolers, if I was to lay one of these hard drives end on end, how long would the line be until I got 140 petabytes of storage? And they threw various guesses out, and it's actually 13 miles, right? So that's how long it would take.
We had something
pulled,
like that at NCI, Doug. Sorry to interrupt. Years ago, I don't remember the exact analogy, but it used whatever the current storage was on an iPhone at the time and our archive volume. And if you stack these iPhones up it was basically
Yeah.
like it would reach to the moon or something like that. But sorry.
All right, you're killing the next part of my story now, Ken, but I'll forgive you. So I then pulled out of my bag a 48K ZX Spectrum, which is the computer I had as a child, right? I just got a clone of it the week before. And I didn't tell them how much storage was. Actually, them finding out how much storage this brick had, and it only had 48K. They didn't even know K was a thing. I said, well, how many end on end do you think that would take? And it's the distance to Mars. Okay. So this thing, which was like twice the size of that terabyte, held 48K. This thing that was the size of a wallet holds a terabyte. So it's not going to be that long before you could envisage that wallet size thing holding a petabyte. And we just need 140 of those, and we could fit those in a big suitcase. Right. So data storage is going to get smaller and cheaper. We'd already demonstrated that, and you made the same analogy. But how much data do you think we're going to need? Like the difference between the 48K Spectrum and the 1 terabyte hard drive was about 40 years. How much data are we going to accumulate in 40 years' time? I can't even begin to imagine. So yeah, DNA-based storage. What's the most durable form of storage known to mankind, Ken? Do you know?
Paper.
Stone.
Oh,
Stone.
it's okay.
Carving
Stone.
it on stone. Unfortunately, you
Paper's
don't
not
get a lot
heavy.
of bite for you don't get a lot of bite for your brick that way. And I can see that we're nearly about at time, so I'm going to shut up. Thank you very much for your time, everybody. Appreciate it. Leslie, take us out.
Okay, we are. No, it's okay. So is that your closing? We have my watch doesn't say we are at.
I saw you hovering, so I thought it was time to shut up.
No, the hovering was just to, just to be together on screen. Would you like to stop sharing your screen and then you can give your closing? Or
That was my closing.
That was your closing. Okay.
My
Well,
anecdote about 48K Spectrums wasn't good enough for you, Leslie. I'm sorry. I'll do better next time.
okay, well, it does. We are headed to lunch here in some minutes, but I'd like to thank everyone, the speakers, the people here in the room. I wish I could just turn the camera, but everyone here in the room, one more round of applause, and thank you for people online as well.